This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on complex numbers in polar form. So normally we're giving a complex number in the form of a plus bi, 3 plus 2i, 5 minus 7i. That's our usual format. And of course recall that I is the square root of -1. Well, in this lesson we're going to think about complex numbers written in a form very similar to polar form, of the form r times cosine theta plus I times the sine of theta. Now, what is r and what is theta? R is the modulus of the complex number, and that's a strange sounding word. More simply, it's the length. So you maybe never have thought of what a length of a complex number is because it doesn't really sit on a number line. But we're going to describe that process. And theta is an angle measured from the x-axis. So indeed, r is going to be the distance from the origin, just like r was in polar coordinates, and theta measured counterclockwise from the x-axis, just like it was in polar coordinates. So this is a direct analog to those concepts. So here we're going to start with a complex number, 3 plus 3i. We want to find out what is its modulus, r, and what is the angle theta it makes with the x-axis so that we can write it in this form. So just to take a quick look at what we mean by this, the x-axis in this world is perceived as the real axis, and the y-axis is the imaginary axis. So 3 plus 3i, 3 units in the real direction, 3 units in the imaginary direction. Once we're there now, this is the complex number, starting at the origin and ending at that red dot. That is a complex number. We can certainly find its angle using techniques from trigonometry. We can also find this angle theta using techniques from trigonometry. So what do? We're going to call this complex number 3 plus 3iz. It's traditional to use the letter z to represent complex numbers. And you'll see that the length of z squared, the hypotenuse squared, is the x value squared plus the y value squared. Well, the x length is 3 and the y length is also 3. So we get 3 squared plus 3 squared, 9 plus 9, 18. So the modulus, the length of z, will be the square root of 18. Just one warning, don't plug in 3i for the y value because we want the length of the triangle. 3i quantity squared is -9, and that is not going to lead us to the correct solution. So again, the modulus of z is root 18, root 9, root 2, or 3 root 2. So that is the distance from the origin. Sounds a lot like r from polar coordinates. Next up, we've got to measure the angle theta in that triangle. Reminding you, of course, that the modulus of z is the r that we used in polar coordinates before, is the r we're using in this formula. But to solve for theta, we're going to take the tangent of theta is opposite over adjacent. The length of the opposite side is 3. The adjacent is also 3. Tangent of theta is 3 over 3. Tangent of theta is 1. Then what is theta? Theta is 45 degrees. So we have our angle theta there. We have our length here. So we can think of this complex number z is 3 plus 3i as r, 3 root 2, times cos pi over 4 plus I times the sine of pi over 4. Or cos 45 plus I times the sine of 45. And you may argue that this looks more complicated than this. Well, the same way that polar coordinates in some ways were more complicated than Cartesian coordinates. But polar coordinates gave us some advantages. And you'll see very clearly what the advantages are to this form, this r cos theta plus I sine theta form is compared to that form. So let's take a look at our next example. We want to convert -2 root 3 plus 2i to r cos theta plus I times the sine theta form. -2 root 3 this way, -2 root 3 in the x direction. In the real direction, 2i, 2 in the imaginary direction, so this now is our complex number. R will be the length of this hypotenuse of this triangle, and theta measured from the x-axis. Remember, that's how we are measuring theta, measured counterclockwise from the x-axis. So what can we say about this? The magnitude of z, or the modulus of z, is that r. The modulus of z squared, the hypotenuse squared, is the x guy squared plus the y guy squared. Now whether you use -2 root 3 or +2 root 3, I don't really think makes a whole lot of difference. But the y value has to be 2 and cannot be 2i. 2 squared is 4, root 3 squared is 3, 4 times 3 is 12. we get 12 plus 4, or 16, for the modulus of z squared, which then tells us the modulus of z is 4. And I'm using the modulus of z instead of the polar form of r, but they mean the same thing. Now how about the angle? I'm looking at the reference angle here first. That's an acute angle. The tangent of the reference angle here is opposite over adjacent. The opposite is 2. The adjacent, in terms of its length, is 2 root 3. So for the little reference angle right here, I get the tangent of the reference angle is 1 over root 3. So the reference angle is pi over 6. We know that. But our angle theta starts at 0 and moves to that point. So that's pi over 6 short of pi. So that the theta I get here should be 5 pi over 6. So we've done that. We have our modulus of z is 4. We have our theta is 5 pi over 6. We have indeed successfully converted this into that form. So z is 4 times the cos of 5 pi over 6 plus I times the sine of 5 pi over 6. But I haven't shown you why this is valuable. Well, it's valuable when we are multiplying complex numbers, dividing complex numbers, and raising complex numbers to powers. So let's take a look at that. I have this complex number, z1 is 6 cos 50 plus I times the sine of 50 degrees. z2 is 4 times the cos of 160 degrees plus I times the sine of 160 degrees. Now we don't know what these values are. These aren't things we have memorized or that we use fairly often, but when we combine these things, we will not need a calculator to solve. Fortunate in this case that that's the way it worked out. But here's our basic idea. When multiplying two complex numbers, multiply the moduli, this modulus 6, that modulus 4. We're going to multiply the two moduli and get 24, and then add the angles because we're rotating around. First we rotate 50 degrees from the x-axis, then we rotate another 160 degrees. As we rotate, it grows. So we've rotated a total of how many? 50 plus 160. We've rotated a total of 210 degrees. So using this, multiplying the two complex numbers, the modulus of the product is the product of the moduli. The first modulus times the second modulus, 6 times 4 is 24. So that's the length of the new vector, z1 times z2. My angle is going to be 50 degrees plus 160 degrees. We're going to add those two things together. So my new angle is going to be 210 degrees. And that'll be our angle theta that we'll use. So we know z1 times z2, multiply the moduli, 24, cos 210 plus I times the sine of 210. Hey, 210 is nice. That's 30 more than 180, and it's one that we can analyze. Cos 210 is negative root 3 over 2 because the reference angle is 30 and we're in quadrant 3. Sine 210, reference angle is 30 and we're in quadrant 3. That's negative as well. And simplifying that, we get negative 12 root 3 minus 12i. So multiplying complex numbers in polar form is relatively easy. Multiply the two moduli and add the angles together. And then do your simplification. Now division is similar. In this situation I have z1 is 12 cos 110 plus I sine 110. z2 is 2 cos 50 plus I times the sine of 50. And I want to divide those. So we'll take z1 divided by z2. What will that give me? Well, our rule here is to divide the moduli. So 12 divided by 2 will be 6, and then subtract the angles. So similar to the multiplication, if I'm dividing those two guys, the modulus of the first is 12, the modulus of the second is 2. 12 divided by 2 will be 6. We know that. And then subtracting the angles, 110 minus 50 is 60. So we have 6 times cos 60 plus I times the sine of 60. And what does that give us? Cos of 60 is a half, sine of 60 is root 3 over 2. 6 times a half is 3. 6 times root 3 over 2 is 3 root 3. And you see what we're going to get there. We're going to get 3 plus 3 root 3i. So doing our division there, using our properties of complex numbers, that also works out fairly easily for us. Now with powers, we want to use this technique or this process of DeMoivre's theorem. So we're going to first convert this into polar form, and then we'll see how to handle powers of complex numbers. So here we've got what? We want to take 1 plus I to the 6th power. So that's 1 unit in the real direction, 1 unit in the complex direction. So maybe it's obvious what that angle is, maybe it's also obvious what that modulus is, but let's quickly do the analysis. So the modulus of z is that r, that is the hypotenuse. The hypotenuse squared is x squared, 1 squared, plus y squared, 1 squared. So the modulus squared is 2, so the modulus of that complex number is the square root of 2. That's the length. Now what about the angle? How can we get that? Tangent is opposite over adjacent, 1 over 1. Tangent of theta is 1. And theta is pi over 4 again. So what we have here is we can rewrite this 1 plus I as square root of 2 times cos pi over 4 plus I times the sine of pi over 4. We have that for our value z, which is 1 plus I. But our question is asking us to raise that to the 6th power. So we've got to take this thing and raise it to the 6th power. Well, we knew with multiplying, you multiply the modulus. So we're going to multiply this to the 6th power, multiply it by itself 6 times. And we also saw that when you multiply, you just go ahead and add the angles. So pi over 4 on the first twist, then another pi over 4, then another pi over 4, then another pi over 4, etc., until we have 6 of them. So the process is just a generalization of what we did with the multiplication. So where does that put us? Here's our basic idea. You're going to raise a complex number to the nth power, raise the modulus to the nth power, and multiply the angle by n, because you're doing that same angle n times. That's going to be our idea. What do we have here? We had our z, which was 1 plus I is the square root of 2 times cos pi over 4 plus I times the sine of pi over 4. We want to raise that to the 6th power. So z to the 6th, or 1 plus I to the 6th, will be root 2 to the 6th. Cos pi over 4 plus I times the sine of pi over 4 to the 6th. And what will that be? Root 2 to the 6th, and then multiply that angle in 6 times. Now 6 times pi over 4 is 3 pi over 2. And root 2 to the 6th power is, I believe, 2 to the 3rd power. Root 2 is 2. And then another root 2 is 2. And another root 2 is 2. So we have 8. This piece is 8. Or 2 to the 6 halves. 2 to the 3rd is 8. So we get 2 to the 3rd cos 3 pi over 2 plus I times the sine of 3 pi over 2. Always think about the unit circle. 3 pi over 2 between the 3rd and the 4th quadrant downstairs. Cosine is 0 and sine is negative 1. So we get 8 times 0 plus I times negative 1, which of course is just negative 8I, or 0 minus 8I if you prefer. That'll be how we would express that complex number in a plus bi form. And that will conclude this lesson.